Hey bro, today we got a new reasoning algorithm update. With this update we are more intelligent. Ooh.
Or if you are not a bold, ugly American YouTuber who has no education and just shout in your microphone, we can use our intelligence, and because we are beautiful, young and gorgeous, we can talk in a normal voice about enhancing here the reasoning capabilities of LLM during inference for a better complex reasoning. So, we will discover a new methodology for test-time reasoning enhancement, where we'll combine a search-based algorithm and a reward-based feedback to solve real complex tasks in mathematics and logic. We will overcome this old limitation by the old system here of chain-of-thought reasoning, self-consistency, self-rag. You see, a year ago I did this video, by simply a new balance of the exploration and the exploitation of the possible solution space, enabling here a structured and a better informed decision-making by our reasoning step after the LLM to be dynamically evaluated by the system itself during the inference run. And this is something beautiful. We have here a new report, November 18, 2024, Technical Report on Enhancing the LLM Reasoning with Reward-Guided Tree Search. This is the paper, if you're interested, that gives you here the new main idea to enhance the reasoning in LLM by guiding here the decision process through a tree search approach supported by a reward model that scores the action and a new policy model that adapts here the reasoning step in parallel. So we have a new method, our reward-guided tree search framework, where we have three elements: a policy model that is trained to align with the reasoning formats, a reward model providing an outcome level or process level feedback, and a simple Monte Carlo Tree Search algorithm to explore here a broader solution space much more efficiently. The unique feature is here that the policy model and the reward model are trained together, thereby refining each other's capabilities. What we achieve is we can expand now the solution space during our inference run of the LLM, but of course we have to trade in something. So we go here, we're trading in the computational cost and the time that it takes for our LLM to do this calculation for an improved accuracy. And you remember OpenAI model when it was thinking for about a minute or minute 30 seconds here. So we trade in the computational cost that will increase for a better answer. So currently here, everybody is trying here to improve on the performance of O1. Let's have a closer look at our policy model that is trained now, of course, to align with the reasoning format. A reward model providing here the outcome level or process level feedback on our Monte Carlo Tree Search. Now, at first, the policy model. The policy model has now a new job to generate reasoning step in a structured format, and this format has to be compatible with the tree search algorithm by Monte Carlo. So, we have to train this policy model to be able to do this. So we have an instruction tuning. So this means it adapts the model to produce step-by-step reasoning steps that are now aligned with our mathematical problem-solving structure, and improve the policies with feedback from the reward model, ensuring here better decision-making during the search process. The reward model, on the other hand, scores now this intermediate step, or then the final solution, to guide here the tree search process with specific scores. And this is happening in the inference run, but of course we have to train this reward model to be able to do this. Therefore, our reward model has to be configured to provide here a descriptive evaluation of the solution quality. It will focus primarily on evaluating the correctness of the final answer and assigns an absolute reward score to a specific action, thereby enabling an effective guidance for the search algorithm that comes next. We have here in the simplest case a Monte Carlo Tree Search approach to explore here the vast reasoning space much more efficiently. And the enhancement include here a self-consistency evaluation and finally a tool integration that verifies here the computational step using here external tools. For example, here some Python files for mathematical computation. Finally, they integrate here the tools for the job. Let me give you a feedback on some comments I received from some subscribers. And they always tell me, hey, just give me the code. Don't explain anything to me. With code, I have a computer. I just want to play with the code. So let's have a look at this. You have the code level. Now the code level is simply the code, let's say in Python, is written today by Cursor or Windsurf, by Codium, or if you're an old-fashioned guy, you go with the GitHub Copilot from Microsoft. I don't know how many plus are currently with Microsoft Copilot, but you get the idea. And you know all those AI pattern recognition systems have been trained on I don't know how many million GitHub repos where we have the code sequences, and the machine simply reproduces here the code from all the different GitHub repos given here a specific task. So, code is written now by our systems, and it will improve in the next 3 months, 6 months, and a year even better. Now, you ask how to optimize the code, how to improve now a performance of a system of our LLM. And then you ask me, hey, we need new code from you. Can you give us new code? Now, this is interesting because code is just the implementation of an idea. So code is just the formalized representation, if you want it a little bit more precise, of a new method to solve a problem that you encounter. So if you want, we have here the code level or the code space, and above the code space, here's what the code is representing here. And above the code is the space of new ideas, of new methods. So understanding why your code fails is not that the code sequence itself fails, trying to approximate or find a solution to your problem, but the idea behind the code, the methodology you apply for a particular problem, is not adequate. The idea, the methodology is maybe outdated, and it is not up to the task. So it is not that the code is wrong, it is just that the methodology that is then encoded in a formal computer language, that this methodology is not as powerful as you need it. It is not on the code level. What this means here, if we have the space of new ideas generate new code implementation. And I mean, Windsurf or whatever you have will generate the code for me. Because the code implementation is simply given here in our how many million GitHub repos, and then it is just by a pattern matching machine like Cursor or Windsurf or Copilot that generates the code for me. So code generation is not the topic. New ideas that will manifest in code representation. This is the challenge. Because the translation from the idea to code, if I have the idea, this code generation is automated. Go with A, B, or C. So this means the space of new ideas is now something that is absolutely unexplored. Every day we have up to 800 new AI research publications where people present new ideas. Some of them are already coded, some of them are absolutely just on an abstract level, maybe just an abstract mathematical structure. But if you can code this, and if you use tools like Cursor or Windsurf or Copilot, this is done automatically, but you have to understand these ideas and you have to understand how to combine those ideas. And this is here the positioning and the core of my YouTube channel. Great, let's come back to the main topic. The technical report on enhancing LLM reasoning with reward-guided tree search is here. This is here within a much broader topic of test time scaling, which expands here the reasoning capabilities by using more computational resources, as I showed you, for a more dynamic solution exploration, evaluation, and final results. Now, let me be clear, this goes beyond our classical TTT, our test time training, and it aligns much more closely with a searched enhanced inference strategy as those inspired by AlphaZero. Now, you remember in the good old times of 2023, we were talking about a tree of sorts, and this was here a very, very old methodology, and you have here the code, of course, by Princeton and Google DeepMind, and this is now 1 year later. We come back now and we have now a reward-guided tree search. And this is not an easy idea to understand, and the code is done automatically. So we're building up here of the insights from 2023. And of course, you remember here just a week ago, November 11, 2024, we had MIT here with this interesting publication here for the TTT, the test time training here for abstract reasoning. And I will do my next video probably on this article, but just to tell you what is it, LLMs are updated to an explicit gradient step based on the test time inputs, and it differs here from this, what you know as a standard fine-tuning process as it operates here on extreme low data regime. Yeah. Just to tell you, both methodologies here share the same idea of leveraging additional test time computation to enhance the system performance. While TTT focuses here on fine-tuning the model parameters during the inference to adapt to new test data and fight a domain shift. The reward-guided tree search, that is the main topic of my video today, relies here on a pre-trained model and uses here the search algorithm to dynamically guide the reasoning without altering the LLM weight tensor structures. Of course, if you want to have a preview into the TTT origin, I think you read this paper from 2017. This is University of Edinburgh, and Ben Krause is here the main author. Real nice. It's called the dynamic evolution and fits well to the recent sequence history, allowing them to assign higher probabilities to reoccurring sequential patterns. You see, TTT in this terminology was not invented, but this is here the classical origin of our TTT as we know it today. So, also both approaches here involve here the test time adaptation, aiming to refine here the model performance during the inference, and this really have to stress here during the inference run rather than training time alone. But our reward-guided tree search trades off here the computational cost for better reasoning by here exploring here the solution spaces. So we have a different search methodology than just TTT. Great. So this reward-guided tree search now outperforms the baseline methodologies as the chain of thought reasoning, and it works great on these challenging data sets that we have in our benchmark. And I will show you the results a little bit later on. Main element, co-optimization of the policy and the reward models. It demonstrate here a general improvement enabling here refined reasoning and evaluation strategies. And you can even optimize here our Monte Carlo Tree Search with an extended Monte Carlo Tree Search by considering now all leaf node during the exploration here for a broader coverage. And here we are with the summary. We now implemented here the idea of a test time framework, leveraging here 3 elements: a policy model for the step generation, the reward model for the feedback to the policy model, and then a simple Monte Carlo tree search algorithm for the structured exploration of all generated solution. So this is it in a nutshell. However, if you want to know more, this is the second part now with a much more detailed view with a little bit deeper understanding. So let's focus at first on the policy model, and I will treat the policy model in combination with the reward model because, as I told you, both are trained here in tandem and they have a real immediate feedback. So the policy model is the core component here of this reward-guided tree search framework. But of course, that it works, we have to have a training process on our domain-specific data that we do not have domain shift and. So training process, you have more or less 2 steps. You have an instruction tuning for reasoning format adaptation and a preference optimization for the policy improvement. You know PPO maybe, and we will use DPO. Let's start here with the first step. So the first step is instruction tuning for reasoning format adaptation. So we want that our policy model produce here a reasoning output structured now as a multiple step tree-based process suitable here for our new search algorithm. Therefore, we have to have a format definition of the output. Each reasoning step in this output is represented as a node in a tree structure, and each step involves logically complete reasoning, which may span multiple sentences in, let's say, a mathematical or a logical context. So the output format that we are looking for has a problem reformulation, a step-by-step reasoning process, and the final answer has a structured format like here, this box parenthesis. Format definition, done. Next step, data synthesis. For data synthesis, here the authors say, hey, we need now a bigger model. We need here big brother AI to teach our little model here, because what we need here is a real high quality data set for the training process. So the authors go here with QN 2.5 Math 72B instruct, and the training data set is now populated with well-structured and logically improved sound reasoning paths. So what it does, it just enables here the policy model in the training phase to learn from higher quality examples, aligning it with the required reasoning format definition. Because we want that the policy model has, if you want here, the training from the best possible world, from the best possible model, to reflect the optimal reasoning strategies that are maybe beyond the LLM that we use here. So we need here one of the best models on the planet, and that the examples are diverse enough to cover different approaches to solve a problem and are correct and free from common LLM errors. Data synthesis, check. Next step, the fine-tuning itself. Now we have the training data, so this synthesized training data now are used to fine-tune the policy model. And I've given you the official prompt template that was published by the authors. Now, the next step after we have the fine-tuning, we go now here to a reinforcement learning, and we will apply here a DPO process. So, preference optimization for policy improvement. Here you have 3 videos where I explain what it is, and I give you the code. Plus here you have another 3 videos if you want to apply it here to member systems. Here, if you want, we have 3 particular steps for the feedback from the reward model, training the data construction, then the direct preference optimization itself, and we have an iterative optimization. Let's have a look at this. So, training data construction, again, we have here multiple solutions are generated for each single problem using now our fine-tuned policy model. Remember, we just created here this fine-tuned policy model in the steps before. Now, we have a little bit of cleaning to do, but then those multiple solutions are scored now by our reward model and compared here with our test ground truth answers. So what we get here, we get positive and negative sample pairs, and these are the training data we're going to use. So we have here cleaned up and optimized here our positive and negative training data. Then we have, of course, the DPO process itself, where we have an optimization objective is applied to encourage the model to prefer our higher quality solutions. Remember, from Big Brother, improve the generation quality without diverging too far from its baseline capabilities. Our, if you want, alignment process sets in that we know here, and we have the standard code implementation from Hugging Face. And then the policy model is now refined iteratively in conjunction with the reward model. And I think this is here the beautiful part now, this iterative optimization of both models. So the improvements in the reward model directly will enhance here the preference optimization process, creating here a feedback loop for the mutual reinforcement. Isn't this beautiful? Both models work together, both models optimize themselves. So what we have achieved now, the outcome here of the policy model training, the model reliably now is able to generate step-by-step reasonings that align with the structured tree format that we need now, because now that we have so many possible reasoning paths in front of us, we need now a tree format, or need now a Monte Carlo Tree Search algorithm, a little bit advanced one, to come to the correct solution. So, preference optimization ensures that the model prioritizes the higher quality solution during the reasoning. Nice. And now to the final part, the tree search algorithm. It is the classical Monte Carlo tree search that you know. It's, of course, crucial of the reward-guided reasoning framework. It allows the policy model now to dynamically explore the complete solution space by expanding the space, evaluating the quality, and refining potential reasoning path during the inference run of our LLM. And this is, if you want, the beauty of this new methodology, that this is all now possible during inference. So, integration with the tree search, what we already talked about. The trained policy model is designed to work seamlessly with the tree search algorithm. This is why we had all this specific format structure. And by generating locally coherent and diverse reasoning step, now this is here the foundation for the exploration and the evaluation within the search framework. And this enhances here the model ability to solve complex reasoning tasks in mathematics and logic and causal reasoning. So just to be clear, the purpose of this tree search algorithm is simply to explore the reasoning space systematically. And we, as always, we have an equilibrium, and we're balancing here, the system balances here of the exploration of new unknown path and the exploitation of promising path that we know that could be guiding us to the correct solution with a high probability. As always, it is here with this tree search algorithm, this balance, exploration, exploitation. So to refine now the reasoning process by iteratively evaluating and expanding the reasoning step, guided by the feedback from the reward model, we have achieved now an understanding of this new methodology. Isn't it beautiful? If you're not really familiar with the tree search algorithm, here's a short refresher. Beautiful, powerful new methodology to enhance the reasoning, exploring, refining reasoning path, and it should mimic the human-like thinking. If you will see here the graph and the explanation in the original study, of course, yeah, here you have it. Now what about the results of this system? Going here to the benchmark data, I just give you here 2 results. It has here for the test a higher accuracy than the other models, and even if you go from some particular models here, it nearly doubles here the system precision compared to the chain of thought reasoning. So, seems like this model is working. So here we achieved our goal, our target here. We attempted here to reproduce OpenAI O1-like reasoning system, where we trade in here the computation time and the computation resources for a better quality of the answer. Great. Now, just for fun, if you made it to the end of the video, you get a bonus. You can have another view on this. No? And this is a little bit like a challenge here. No? Think about it in this way. The policy model is, if you want, the detective who formulates here step-by-step solution. No? It is a little bit like Sherlock Holmes outlining his deduction and explaining how he arrived at his conclusion. And our model here operates in a tree-like space where every decision is a branch towards a potential answer. Now, the reward model, if you want to judge here, is our Watson. So this model here evaluates every reasoning step, assigning here scores to decision, providing a feedback to keep the detective here on track, give feedback to Sherlock Holmes. And it doesn't, Watson doesn't say yes or no, but it tries to argue. It gives here a nuanced score, weighing here local correctness and alignment with the final goal. So Watson is a little bit here of our lighthouse, and it tries to make sense and behave human. And then, of course, we have our tree search algorithm. And if you want, this is here the mastermind who plots the course, who dynamically now adapts to the feedback, ensures that the detective doesn't chase here dead ends or overlooks key evidence. And this player now turns here the reasoning into a game of exploration and optimization, exploitation, balancing here the risk with the evaluation results. If you want to see it in this different perspective, it is the same topic, but maybe it is a little bit more accessible to you if you like Sherlock Holmes and Watson and our mastermind behind all of this. And yeah, I mean, if you really want to go and be now much more scientific, you know that this paper offers now a beautiful bridge, because you know what? With this new idea, you know, I've talked to you about the idea space and the code space. And if we're in the idea space, this reasoning that we just encountered, we could model as a dynamic quantum system analogon. But of course, I know what you're gonna say. You say, hey, this video was long enough, and yeah, please postpone this maybe to a later video. And as a subscriber, I will be noticed when you publish the next video. Would be great to see you then.